In this talk, I will talk about efficient list decoding with constant alphabet and list sizes. So let's start with the notion of Arcadian codes. An Arcadian code or code C can be seen as a subset of sigma to the n, where sigma is a finite size called the alphabet, and n is called the code word length or the block length of the code. The elements of the code C are called the code words of the code. And the code has some parameters that measure how good the code is. One is the rate of the code, which measures the redundancy in the code. Another important parameter is the minimum distance or relative minimum distance of the code, which we denote by delta. It's defined to be the minimum possible distance between two distinct code words, where the distance between two code words x and y is defined to be the fraction of coordinates where x and y differ. And in this talk, we will focus on list decoding of Arcadian codes. List decoding is a relaxation of the standard notion of decoding, where we allow the decoder to output a short list of candidate messages that contains the transmitted message instead of just outputting one message. And the advantage of list decoding is that by allowing the list to contain more than one message, we could correct a large fraction of errors, which may even exceed half of the minimum distance. And this property turns out to be very useful in theory of computer science and has found applications in complexity theory, cryptography, linear theory, etc. Given that list decoding is useful, our goal would be to construct a good list decodable codes, which means the following. Ideally, we want to construct codes with rate R that are list decodable up to radius that is close to 1 minus R. This radius is the best one can hope and is called the list decoding capacity. And we also want the code to have small list size and small alphabet size. Finally, the code should be explicit in the sense that there is an efficient encoding algorithm, and hopefully there is also an efficient list decoding algorithm. And if we ignore the last condition about the explicitness and efficient list decodability, then the existence of good list decodable code follows from the list decoding capacity theorem, which is proved by simply the probabilistic method. It states that for any r and epsilon between 0 and 1, there exist non-explicit codes of rate r that are list decodable up to radius 1 minus r minus epsilon, with list size O1 or epsilon and alphabet size 2 to the O1 or epsilon. So these codes achieve the list decoding capacity, and we say they are capacity achieving codes. And the list size and the alphabet size depend only on the parameter epsilon. So if epsilon is a constant, then the list size and the alphabet size are both constants. So this theorem guarantees the existence of list decodable codes with very good parameters. However, these codes are not explicit codes. So we can ask whether there exists explicit capacity achieving listicle codes with similar parameters. In particular, we hope the list size and the alphabet size are both constants, depending only on the parameter epsilon. And constructing explicit capacity achieving listicle codes turns out to be highly non-trivial. For example, we can look at the Reed-Solomon codes, which is one of the most well-studied Arcadian codes, and it's defined by an encoding map that sends a low-degree polynomial f to the evaluations of f at n evaluation points, alpha 1 through alpha n. And Goswami and Sudan prove that Reed-Solomon codes are efficiently decodable up to radius 1 minus square root of r, which is also known as the Johnson bound. And note that this is worse than the list decoding capacity. So one question is if Reed-Solomon codes are list decodable beyond the Johnson bound. And Ruja and Wouters were the first to prove that with hyperability, a random resolvent code is combinatorially least decodable beyond the Johnson bound. It's combinatorially least decodable in the sense that we have a good bound for the list size, but not necessarily an efficient list decoding algorithm. So we know random resolvent codes can go beyond the Johnson bound. However, it's still an open problem that if random resolvent codes can achieve least decoding capacity, let alone constructing explicit resolvent codes that achieve the capacity. And the first explicit least decodable codes that achieve the least decoding capacity were constructed by Goswami and Rudra, known as the folded Reed-Solomon codes. A folded Reed-Solomon code is obtained by combining m symbols of a Reed-Solomon code into one symbol, where m is of order 1 over epsilon square, and such code is least decodable up to radius 1 minus epsilon. And here is an example when m equals 3, and here each column represents a symbol of the folded Reed-Solomon code, which contains m symbols of an ordinary Reed-Solomon code. And while folded Reed-Solomon codes achieve the least decoding capacity is alphabet size is n to the O1 over epsilon square, where n is the block length of the code. So its alphabet size is unbounded and depends on the block length. And the list size was originally also bounded by a function that depends on the block length of the code. And later, Carpati, Ranzavi, Seraf, and Wouters showed that the list size can be bounded by 1 over epsilon to the O1 over epsilon, which is a constant depending only on the parameter epsilon. And other than the folded Reed-Solomon code, Goswami and Shin use algebraic geometry codes to give an explicit construction of a capacity achieving least decodable codes. And the alphabet size of their code is exponential in tilde O1 over epsilon square, which depends only on epsilon. However, the list size that they obtain is triply exponential in log star of n, which grows very slowly in. Still, it depends on the block length n of the code. And I also want to mention another construction given by Kopati, Ranzavi, Seraf, and Wouters based on multi-level concatenation for the Reed-Solomon code, plus a technique called expander-based amplification. The alphabet size of this construction is 2 to the poly 1 over epsilon, and the list size is tau in 1 over epsilon. Still, both parameters are constant, depending only on epsilon. And the encoding algorithm has time capacity that is polynomial in n, but exponential in 1 over epsilon. Okay, now we are ready to present our results. We give an explicit construction of codes of rate r that are least decodable up to radius 1 minus r minus epsilon, which achieves capacity. And the list size is 2 to the poly 1 over epsilon, and the alphabet size is 2 to the tilde O1 over epsilon square. So both the list size and alphabet size depend only on epsilon. Moreover, the encoding time of our code is polynomial in n and 1 over epsilon. And for decoding, we show that the list of candidate messages is always contained in a subspace of the message space, and this subspace has dimension poly 1 over epsilon, and the basis of this subspace can be found in time poly n 1 over epsilon. And if we want to output the whole list, we can just enumerate all members of this subspace and check if each of them is in the list one by one, and this takes time 2 to the poly 1 over epsilon times poly n. So this is the time capacity of the list decoding algorithm. And this is our statement of a result. And our construction is based on the framework developed in the work of Goswami and Shin using algebraic geometry codes. And one key new idea is the use of what we call BTT subspaces, which I'm going to explain now. Here's the definition of BTT matrices and BTT subspaces. We define a KMR block triangular Topliss matrix, or a BTT matrix, over field F to be a KM by KR full-rank matrix over F that is both block lower triangular and block Topliss as a K by K block matrix. Here's an example. When K equals 4, we have a 4 by 4 block matrix, and each block is an M by R matrix. As you can see, this matrix is block lower triangular, and it's also block Topliss, meaning that on each diagonal, the blocks are the same. And note that the KMR BT matrix represents a linear map from F to the KR to F to the KM, and we define KMR BTT subspace to be the image of such a linear map represented by a KMR BTT matrix. Okay, so these are the definition of BTT matrices and BTT subspaces. Next, let me give an overview of our construction. It's based on the framework developed by Goswami and Shin using algebra geometry codes. We choose the alphabet sigma to be a vector space Fq to the M, where Q and M both depend only on epsilon. And our construction has two steps. First, we construct a preliminary capacity-achieving list decodable code C prime, which has the property that the list of candidate messages is always contained in a small BTT subspace. And this BTT subspace is small, but its size is not constant. So this property itself does not imply a constant bound for the list size. This is why we need to the second step. At the second step, we construct an explicit subspace W of the message space such that W has local dimension. And also it has a property that it evades BTT subspaces, meaning that the intersection of any BTT subspace with W has constant size. And our final code is obtained by restricting the message space of C prime to W. Then the list of candidate messages of this final code is always contained in the intersection of W with the BTT subspace. And since W evades BTT subspaces, we know that this intersection has constant size. And this gives a constant bound for the list size of the final code. So this is the overview of our construction. Next, let me give you some more details about these two steps. At the first step, we construct a preliminary code C prime. And for this step, we follow the work of Goswami and Shin and construct C prime as a so-called algebraic geometry codes or AG code with subfield evaluations. So AG codes are generalization of Reed-Solomon codes with the advantage that it's possible to achieve constant field size, alphabet size, even if the block length n is unbounded. And what we call an AG code with subfield evaluation is a special AG code that is defined. It's an AG code that is defined over an extension field Fq to the M, but the evaluation points come from the base field Fq. And following the analysis of Goswami and Shin, we show how to construct such a code such that is list decodable up to capacity, and the list of messages is contained in a BTT subspace. And this factor was also independently observed by Goswami and Shin, even though they did not further explore it. And at the second step, we construct an explicit subspace with the property that its intersection with any BTT subspace is small, and we call such a subspace a BTT evasive subspace. Formally, the KMRS BTT evasive subspace is a subspace W such that for any KMR BTT subspace V, the intersection of V and W has dimension at most S. And in our paper, we pull a theorem which gives an explicit construction of a BTT evasive subspace W that satisfies our requirement. In particular, the codimension of W is small, is of order epsilon km in an ambient space of dimension km. And the parameter S, which is the upper bound of the dimension of the intersection, is polynomial in 1 over epsilon. And then we restrict the message space of the preliminary code to this BTT evasive subspace W. So such a restriction does not reduce the rate of the code by much, since the code dimension is small, and the new code the new code is still capacity achieving, and the list size is reduced to q to the s, which is exponential into the O1 over epsilon square, as claimed. So everything boils down to proving this claim. And to explain our proof of this theorem, we need another notion called the periodic subspaces. These are relaxation of BTD subspaces. Recall that BTD subspaces are images of linear maps represented by BTD matrices. Similarly, we define periodic subspaces as the image of linear maps represented by periodic matrices, where periodic matrix is a relaxation of BTD matrix. So for periodic matrix, we no longer require the blocks on the same diagonal to be the same, but only require the blocks on the main diagonal to be the same. Those blocks below the main diagonal can be anything, as shown in this picture. So these are the definition of periodic matrices and periodic subspaces, and we can also define periodic evasive subspaces, just like how we define BTT evasive subspaces. And a beautiful paper by Goswami and Kobati gave an explicit construction of periodic evasive subspaces. And then this construction, this theorem is based on pseudorandom objects called subspace designs. And note that a periodic evasive subspace is automatically a BTP evasive subspace because periodic subspace generalize BTT subspaces. This means the construction of Goswami and Kobati also gives a BTT evasive subspace, which is what we want. However, this construction itself is not good enough for us. This is because the parameter k that they can achieve, which is a number of blocks in the BTT matrix, is only polynomial in the field size q. And because we work over the fields of constant size, the parameter k we get is too small for us. So this construction does not directly gives us what we want. However, it's still useful as a building block, but we need other ideas. And another idea we use is a composition technique, again introduced by Goswami and Shin. They implicitly show this lemma, which we call the composition lemma. Suppose W is a KMRS periodic evasive subspace, and W prime is a K prime KMSS prime periodic evasive subspace. We define the composition of W and W prime to be the intersection of W to the K and W prime. Then the composition lemma states that this composed subspace is K prime K MRS S prime a periodic evasive subspace. And this technique of composition can be seen as an analog of concatenating an inner code with an outer code in coding theory. And motivated by that, we call W the inner subspace and W prime outer subspace. Given the composition lemma, we could use the construction of Goswami and Kobati to construct an outer subspace, so that we reduce the problem of constructing the BT evasive subspace to periodic evasive subspace to the problem of constructing an inner subspace. And this reduces the parameter k to O log k. At the same time, it increases the s to poly s. And we could repeatedly apply the composition lemma to reduce k to O log k and then to O log k and so on until it becomes constant. And in fact, this is the idea used by Goswami and Shin in their paper. They apply the composition log star n times. However, since each composition increases s to poly s, in the end, s would be super constant, and therefore they could only put an upper bound for the list set that is multiply exponential in log star n instead of a constant bound. And to further reduce the list size to constant, we introduce some new ideas. First, we extend the composition lemma by showing that if the outer space is periodic evasive and the inner space is only BTT evasive, then the composition is also BTT evasive. This means that in order to construct a BTT evasive subspace, which is what we want, we just need the inner subspace to be BTT evasive, which is formally weaker than periodic evasive subspace. And then we apply the composition lemma only twice instead of log star n times. This reduces k to log k. And then instead of continuing this chain of compositions, we use brute force search to find a good inner BTT evasive subspace. And normally brute force search would take exponential time, but here it can be implemented efficiently since we have already reduced k to log k, and the function that is exponential in log k is only subpolynomial in k. And we also need to prove that the good BTT subspace exists, and this follows from the probabilistic method. And I want to remark that the existence of such a BTT evasive subspace crucially use the fact that we are working with BTT subspace instead of periodic subspaces. Because if we work with periodic subspace, then the probabilistic method would not imply the existence that would not imply the existence of a good subspace that are evasive against all periodic subspace, because there are too many periodic subspaces, but there are not too many BT subspaces, so the probabilistic method works well in our case. Okay, so this is a sketch of our construction and its analysis. To summarize, our construction has two steps. First, we construct a preliminary code using the AG codes with subfield evaluations. Next, we construct a BTT evasive subspace W and restrict the message space to W to obtain the final code. And here W is constructed using a repeated composition of outer periodic evasive subspaces and the inner BTT evasive subspace. For the outer subspace, we use the composition given by Bruce Flaby and Kobati, which is based on subspace designs, and the inner BTT evasive subspace is found by brute force search. And I also want to remark that this repeated composition technique also appears in other places in theoretical computer science. For example, a well-known construction of the so-called asymptotic good codes is obtained by repeated concatenation of outer codes with an inner code that is found by brute force search. And the original proof of the PCP theorem also uses a similar technique. It's done by repeatedly composing outer PCPs to reduce the size of the problem and then apply one more composition with an inner PCP to reduce the query complexity to a constant. Finally, I want to list some open problems and future actions. First of all, the codes we construct have list size exponential in 1 over epsilon. So one open problem is if we could reduce the list size to 1 over epsilon or anything sub-exponential in 1 over epsilon. And for explicit capacity achieving code, list decodable codes with efficient list decoding algorithms, the best known bound we know is 1 over epsilon to 1 over epsilon, which is exponential. And this is achieved by 4-degree Solomon codes. So this is an open problem even if we allow the alphabet size to be large. And the second open problem is finding explicit list decodable codes achieving the capacity over an alphabet whose size is an absolute constant. In our construction, alphabet size depends on the parameter epsilon, so it's not an absolute constant. If we want the alphabet size to be, say, 2 or 3, then the list decoding capacity, the correct list decoding capacity is given in terms of the quinary entropy function. And finding explicit code achieving the capacity in this case is a wide open problem. And finally, we wonder if our methods, in particular the notion of BTT subspaces and BTT evasive subspaces, could find applications to other problems in pseudo randomness. And one example is, for example, the list decoding technique has been used in constructing lossless dimension expanders. So we wonder if our ideas can also be useful in the study of this problem or related problems. Okay, this is the end of the talk, and if you have any questions, feel free to contact me by email. Thank you for your attention.